Hello, class, and thank you for watching. In lesson 2.8, inverse functions part 1, you're going to determine the input-output pairs of the inverse of a function. And again, correlate it to some questions here. Now, first of all, an inverse function will undo, quote unquote, undo a given relation, a given situation. Every inverse function can be found by switching each x and y value. So as you look over here on the right, this diagram is illustrating this concept. If I have a function f, the x values, which is referred to as your domain, your input values, again, your domain, and the y is your output values. Again, your range. What an inverse function is going to do is just simply switch that where your inverse, this is a notation, f inverse, is going to switch that where the y values are going to become the input to the inverse, and the x values are going to become the output to the inverse. Now, the notation that we use in this course to describe an inverse is to have f be raised to the negative 1 power. And again, the notation would be the same if this was h. H to the negative 1 would be the inverse of h, and so on, okay? Now, in some situations, the process is intuitive. We could see exactly what the inverse is, but other times it's not so obvious. And regardless, in these cases, it's important that we understand, again, the concept, this concept of inverse relations, as they're going to help us, again, tackle a variety of problems. And the concept, again, is that the inverse is switching, again, the inputs and the outputs. Again, so your domain becomes your range, and your range becomes your domain. So for example, let's look at example 1. Let's find the inverse to the relation of the given table. So here we have a relation. And first of all, notice that this relation is, in fact, a function. So note the original table right here on the left is a function because each x value has only one y value. In other words, from algebra 1, none of the x's repeat. So since none of these x's repeat, this table right here, relation, is a function. So we have a function f of x. So I'm going to call y and say that y is, again, f of x. Now, to find the inverse to this function f, the main concept is essentially that I just simply switch this. The x values become the y, so 1, 3, 4, and 6, and the y values become the x, so negative 1, 2, 0, and 2. Now, if you look at the table, however, this table, however, the inverse is not a function. Not, let me write it in red, not a function, because you'll notice that the x value of 2 has two different y values, has a y value of 3 and of 6. So this is not a function, okay? So your x's are repeating. So we can find the inverse to a relation by simply switching the x and y values. So even though this is a function, the inverse itself is not a function, but it's still an inverse. Now, for the second example, we want to sketch the inverse relation of the given graph. Well, the steps to graph the inverse of a function, well, first of all, this is a function. Notice again that the x values do not repeat. Using the vertical line test, I see that the x values do not repeat. The vertical lines only intersect the relation at one location. So this is a function, and we'll call it f of x. Is that you want to list the key points in a table. So right here, I'll have the table for x and the y value. I'll call it f of x. And I'm going to do it horizontally since I have no space vertically. And the key points are going to be, again, these vertices right here where the graph is changing direction. So we have the point -2 and -1, -1, +2, 2, 1, and then 4, 3. So listing those points, I want to create now a new table by understanding again the simple concept that the inverse simply switches the x and y values. So the x values and the y values of the inverse, which we're going to denote as f inverse using this notation here, the x values are going to be -1, +2, +1, and +3. And my y values are going to be -2, -1, +2, and +4. Now I'm simply going to now plot these new points for the inverse and sketch the inverse function. So -1, -2 is right here. 2, -1, +2, -1 is right there. And I'm going to connect those 2 points. The next one is +1, 1, 2. So +1, 2. And then 3, 4. Okay. And the inverse will look like this. Now it's a little premature in identifying this as a function, because when I look at this blue graph, this blue relation is not a function, because when I draw a vertical line right here, I see that the vertical line intersects the x-axis at multiple places. So this is really technically not a function, but it is the inverse. So I'm just going to call it x and y, okay? So this blue graph right here is the inverse to the function that's shown in red. Now, we're not guaranteed to have an function every time we get an inverse. Sometimes we do, sometimes we don't. But again, we see here that this is not going to be a function because the x values are in fact going to repeat. Okay. We can see after graphiness, we see that the x values do repeat, that when x is equal to 2 specifically, we have a y value of -1, and up here at 2, we have a y value of 3. So this blue relation is not a function. Another thing to observe is look at the domain. The domain again has flipped. The domain for the original function are all the x values that go from -2 all the way to +4. The domain of this new function, of this new relation of the inverse, go from -1 to +3. The blue graph again goes from -1 to +3. The x and y values have switched, so the new domain of this function is from here to there. Okay, let's now go over how to find the inverse of a function algebraically. Now, since the main concept is to switch the x and y values, that's what an inverse does. We're going to start by doing exactly that. We're going to switch the x and y variables in the equation. We're then going to solve this equation for y, which means solving for y is getting y by itself. And if the equation is in the form of f of x, we're going to replace the y with the notation f inverse of x. We just simply use this notation right there, okay? So for example, let's look at example 2a. Recall that y equals is the same thing as f of x. So let's write this as y equals 3x minus 7. So we're going to replace the notation f of x with y. First thing we're going to do is replace the x and y values. So we have 3y minus 7, and we're going to have it equal to x. So that's the first step. Switching the x with the y. So we replace the x with the y and have it equal to the x value, which again is y. So we're just switching the x with the y. Next step is to solve this equation for y. In other words, get the y by itself. So here, inverse operations requires us to add 7 to both sides. So 3y is equal to x plus 7. And then that requires us to divide everything by 3. So dividing the left side by 3, that's just going to give us y by itself. X plus 7 divided by 3 will look like that. So there is our inverse. Our inverse is f of x equals to f inverse, our inverse, f inverse, is equal to x plus 7 divided by 3. Now we can rewrite this in several forms. Remember, this right here is an invisible 1, so this is 1x. And we can write this in several forms. We can write this as 1x divided by 3 plus 7 divided by 3, which can also be written as 1 over 3 times x. Instead of having 1 times x divided by 3, we could say 1 divided by 3 and then multiply the x like that on the side, and then plus 7 over 3. This is probably the most recognizable way, because this right here is going to write the equation in, again, a linear term of mx plus b. So that's how you get the inverse, and this is going to be 3 ways of writing the exact same notation for the inverse of f. Let's now look at the second example, part of 2b. Now, to find the inverse to the rational function like this, again, we are going to start by switching again the values of x and y. So right here, this x minus 2 is going to become y minus 2 over this x plus 3 is going to be y plus 3. And we're going to replace the y value with x. So this is now going to equal to x. So remember, y is equal to this. And I'm going to do it just by switching the x's with the y's like I did right there. And this y, I'm going to replace it with x. And I wrote it backwards just so it could look a little bit nicer in terms of solving this equation for y, since we always want to do things again to the right side of the equation or left side of the equation to undo this. Now, the procedure to do and solve this equation is by first doing cross multiplication. We're going to get this value and multiply it with this x up there. So it's going to look like this. We're going to have y minus 2 is going to equal to x, and we're going to multiply that x with y plus 3. So cross multiplication. We're going to distribute this 3 into the parentheses. So on the left, we have y minus 2 equals to x times y, which is just written as xy. And then distributing the x again, 3 times x is going to be 3x, like that. Now, the next step to solving this equation from this point on is that I want the y terms. Remember, I want to solve this equation for y. So I need the y terms to be on the same side. So kind of like letters to the left, and even though this kind of makes sense, numbers to the right. Anything that doesn't have a y, you want it to be on the right side of this equal sign. So I'm going to do a little switcheroo here. I'm going to move this to this side, and I'm going to move the 2 to this side. So that's going to give me y minus x times y, since it's positive on the right side, on the left will be negative, and then positive 3x plus 2. This again will be moved over here, which the negative becomes positive 2. Now, here's the trick with this. I cannot combine these two terms because this term doesn't have an x, so they're not like terms. So this is not going to be like negative 1 xy or something like that. What I can do is use the greatest common factor. I can factor the common factor of y. So this 1y minus xy can be can factor out a common value of y. So if I factor out the common value of y in the first term, dividing out the y here is going to give me simply the value of 1, and factoring out the y term from the second term right here of minus xy is going to give me just the term of negative x. And by doing that, I can now do the same thing that I do with any equation where I'm multiplying the y value with a coefficient. Since these are being multiplied, I'm going to divide both sides by that coefficient of 1 over x. So I'm going to divide 1 minus x. So let me write this over here. Let me continue over here. This is going to simplify out, and I'm going to get that y equals to 3x plus 2 over 1 minus x. And that is your inverse. So using inverse notation, we end up with that. Now, this also has another way of writing this. While this is correct, you could also write this as 3x plus 2. You have negative x plus 1. You could switch the x and the 1 value down here, since we normally write polynomial functions again, or rational functions with the leading and whether the numerator and denominator, we want to write them in order, so by degree. And another way of writing this right here, since we have a negative 1 right here, is not customary to have a negative leading coefficient. I'm going to factor out the negative sign and put it in the middle. And by factoring out the negative sign, that's going to make the x positive. So this becomes positive x. And that's going to make the positive 1 into negative 1. So this is a more common way of seeing this. And that way I can figure out other things. Now I can see that the horizontal isotope is going to be 3. The vertical isotope is located at positive 1, because that's what makes the denominator equal to 0. And we have a reflection, a vertical reflection of this because of the negative sign right there. But this would be another way of writing it. But either way, whether you write it like this, or even like this is going to be counted as correct. Let's look at another example of that. So here we have another rational function. So we have 2y plus 1 over y minus 3 equals 2x. So we switch the x and the y value. Now we're going to solve this equation for y, and we're going to do the same thing. We're going to cross multiply. So 2y plus 1 equals x times y minus 3. Distributing that, we're going to get x times y, and then 3 times x. So there. And we're going to switch the x and y term and the 1 term to the opposite side. So we have 2y minus xy equals negative 3x minus 1. Remember, we're going to subtract this 1 from both sides, so we can move the 1 to the other side, making it negative. And the same thing with this. We're going to move this over here by subtracting the x and y. But just to make more sense again, in simple terms, by switching it over, it becomes the opposite. And the same thing here, by switching this over, this becomes the opposite. Now they have a common factor. The left side has a common factor of y. So if I take out the y, I have 2 minus x, and I have a common factor of y. So I factor out the y. That equals to negative 3x minus 1. I'm going to divide both sides by 2 minus x. Divide this side by 2 minus x. I'll continue over here. And y equals to negative 3x minus 1 divided by 2 minus x. So this is our inverse. Now there's a couple of ways of rewriting this and like quote unquote simplifying it. Notice that the denominator is not in the standard form of a polynomial. So I want the x term to be first, and then plus 2, because this is positive, it will be plus 2. So we can write it like that, and that's acceptable. Now you'll notice that I have a negative and a negative down there. Not a usual nicely way of having those. this can be simplified also. So if I factor out a negative from the top, this becomes 3x plus 1. And if I factor out the negative from the bottom, this becomes x minus 2. So this is another possible way of writing this. And then simplifying the negative sign. So if I reduce and divide the negative signs out, this is going to become 3x plus 1 over x minus 2. So this is another acceptable way. So either of these four notations are all equivalent. They're all the same equation. And they'll all be marked correct, okay? This is probably not the best way though, however, because you have a negative and negative, so you could just simplify this to this. But even though it is equivalent, this is probably not the best way of writing it, okay? This is more common way, of course, without the plus sign right here in the front, just the number 2. Or this way right here. If you do want to get rid of the negative sign, because I usually don't like to see negative signs in the leading coefficient, you can factor out a negative like you did right here. And then in this case, because there's a negative on top and the bottom, you can divide them out and you end up with that. Now, let's go over how to determine if we're given two equations, how can we determine if these two equations are going to be inverses of each other? Now, two functions f and g are inverses if and only if the composition f of g of x equals to the input value x, and the composition g of f of x also gives you that same input value of x. So in other words, everything gets canceled itself out by doing a composition, and the only thing that's going to be left is the variable x. Now, to show that two functions are inverses, we use this definition, and we show that both fog f of g of x and golf g of f of x, both of these equal to the variable x. So for example, let f and g be the functions below. Let's determine if f and g are going to be inverses. So by definition, again, two functions are inverses if this is going to be true, if this composition and this composition is true. So to prove that two functions are inverses, we're going to use that definition. So what we're going to do is do f of g of x, okay? Which remember is the same thing as this, f of g of x, that notation there. So starting from the inside, we're going to get the inside function and plug it into the outside function. So here, we're going to get this function of g and plug it into the x of this function of f. So going from the right to left right there. So it's going to be 2 times 1/2 x plus 3 over 2, and we're going to subtract 3. So I have f of x minus 3, and I'm replacing the x again with g. So to simplify this, we're going to distribute. So 1/2 times x, times 2, I'm sorry, that's equal to 1x. 2 times 3 over 2, that equals 3. And we bring down the minus 3. 1x, which is just x, and 3 minus 3 is equal to 0. So that becomes 0 right here, which obviously we don't have to write. We only get the value of x. So there, we have shown that f of g of x equals, again, simply to the value of x. Now, all we have to do is prove and show that when we do the composition in the opposite order, that this is also going to cancel out the operations and only leave us with the variable x. So let's see. So now we're going to go in the other direction. We're now going to get this function f and plug it into this x on g. So we're going to start by writing g, which is 1/2 times the value of x plus 3 over 2. and replace the x again with function g. So 2x minus 3. So this one is done the exact same way. We're going to start by distributing 1/2 times 2, that's going to equal to 1x. 1/2 times negative 3 is negative 3 over 2. Bring down the plus 3 over 2. And well, these two terms have the same denominator, so I can combine the numerator, and negative 3 plus positive 3, that's equal to 0. So we end up with 0 over 2, which is just 0, which we do not have to write. So just x. And there, we have shown it. We have shown that when we do the composition of f of g and g of f, they both give us the value of x. So that means that g is equal to the inverse of f, or f is equal to the inverse of g. But in other words, they're inverses of each other. Whether we think about g as the inverse of f, or we think about f as the inverse of g. Let's now look at the next example. In example B here, f of x is equal to x squared plus 10, g of x is equal to the square root of x minus 2, where x is going to be greater than or equal to 10. Now, not every function can have an inverse unless, again, we restrict values in the domain. In this example, we're restricting, again, x to be only numbers to be greater than 2. In other words, for the inverse to also be referred to as a function. So this really has no actual significance in terms of how we do the procedure. It's just, again, defining what values we're allowed to have, just so we can show that f in fact has an inverse that's going to be a function, and vice versa, that g is going to have an inverse where that is also going to be a function. Okay, so it just very strictly just for purposes of being able to determine and write that the inverses are functions themselves as well. Okay, but in terms of how we prove this, nothing changes. So here, to prove that f and g are inverses, we're going to first get the composition of f of g, which again means this. So we're going to start by writing f, so which is x to the second power plus 10, and replacing the x value with the equation g, so which is the square root of x minus 10. Now, the square root and the square are inverse operations of each other, so they cancel each other out. So we end up with x minus 10, and negative 10 plus 10 is equal to 0, so we just end up with x. Now let's do the opposite. And let's switch f and g, and let's get the composition of g of f. So g of f of x. So we're going to write g, which is the square root of x minus 10. And in the parentheses where the x is, I'm going to write in the function g. So x squared plus 10. If I get rid of the parentheses by distributing a positive 1, because there's an imaginary 1 right here, and multiplying both of these things by 1, we end up with this. Then 10s cancel each other out, so that's equal to 0. And the square root and x squared, again, are inverse operations, so they cancel each other out, and I only end up with x. So there, we have proven that f and g are in fact inverses of each other. And we can say that either g is the inverse of f, or f is the inverse of g. And again, going back to this right here is just restricting the domain on what values of x we're allowed to use, just so we are able to state and say that the inverse, again, is a function as well, okay? Because in this particular example, if we did not use values of x greater than 10, we would still find, again, the inverse, but we would not be able to just say that the inverse is a function itself and use, again, function notation. That's the only thing, again, that it does. It just gives us the ability to write that. So this, in terms of how we find the inverse or prove that these things are inverses, doesn't really change. And this has to be, again, given to you beforehand. It's not like you have to figure that out yourself. You will be provided and given the information that will gives us, again, the, I guess, the parameters, is to say, to be able to say that the inverse is going to be a function itself. And now let's look at the last example. Similar to example B, there are parameters just telling us that x can equal to 0 and x can equal to 4, just for purposes of us being able to say that the inverse, again, is going to be a function itself, okay? So as long as we, again, recognize this, and this, again, doesn't affect how we determine if these two things are inverses. So let's get the composition of f of g. So I'm going to start by writing f, 6 over x minus 3, I'm sorry, x minus 4, and I'm going to replace, again, the parentheses with the function g. Okay, so I'm going to write x over 6, and then plus 4 in the parentheses right there. Well, to simplify this, in the denominator, the parentheses could be in null, so we have 6 over x plus 4 minus 4. The 4's cancel each other out, so I have 6 over x. And in order to simplify this, the trick for this one to get rid of the x in the denominator here is to multiply the numerator and the denominator by that x. So this gets multiplied with x, so the x's reduce each other out, so that becomes 1. And we end up with 6x divided by 6. So in other words, all I did was simply multiply the top by the x and get rid of it right there. So I just simply flipped it over. And now that I have done that, I can now reduce the 6. So 6 divided by 6 equals to 1. So we end up with 1x. So there, f of g of x equals to the value of x. Now let's go in the opposite direction and get the composition of f of g of x. So we're going to start by writing the function g. And in the x, we're going to replace the x with the function f, which is 6 over x plus 4. I'm sorry, minus 4. Now here, in order to simplify this, we're going to do the same trick that we did over here at the very end. Since we have a fraction with it in the denominator of a fraction, like we have right here, we have a fraction, and in the denominator is a fraction itself. We're going to simplify this by simply flipping and getting this to become multiplied with the numerator. So that's the trick here. So I'm going to multiply 6 with x minus 4 over 6. So again, what I've done in this situation, when you have a fraction in the denominator of another bigger fraction, is that you simply get the denominator, look at the denominator, and get this denominator and multiply with the numerator of the bigger fraction. So that's what I'm doing here. I'm multiplying the 6 with that right there. The 6 is reduced, and we end up with x minus 4 plus 4. The 4's cancel each other out, and we end up with simply x. And so there, since again we get x when we do the composition of f of g, and we get x with the composition g of f, that means that f is equal to the inverse of g, again, or g is the inverse of f, okay? And again, this is just stating that we can think about these functions as the inverse of the other. And the order doesn't matter, okay? Whichever one you write is going to be correct regardless. Okay, well, this concludes again our video and our homework for this topic part 1 on inverse functions. If you have any questions, again, send me a message through Parent Square or email. And like always, I appreciate you watching, and I hope you have a great day. Goodbye.